Hello everyone, welcome to this webinar about how to teach robotics with embedded practice. So my name is Ricardo Tellez from The Construct, and today I would like to share with you one methodology that can help. It maybe is useful for you while teaching robotics to your students in order to maximize their learning, their understanding, and making more efficient the time that is dedicated to teach and to learn for your students. Okay, so I'm going to share with you my presentation. And then remember that you can put questions on the chat that is on this side. Yeah, so let me see here. Yeah, okay. Yeah, on this side. I will be answering your questions as they appear or at some undefined times. Okay, then let me see, what do we have here? This is a ghost. Let me see this ghost get out. So, okay, there it goes. Great. Let's go with the presentation. So what is this webinar for? This webinar is indicated is being prepared for all the teachers, all the professors, all the teacher assistants that need to deliver a class in robotics. And they want to engage their students in their learning and make them easier for them to understand those difficult and abstract concepts. So in this class, we need to learn how to prepare the robotic class that is teaching a complex subject and having the robot in mind from the first moment. Then also is going to include some practice with simulated robots, and also practice with real robots. And also we will include a way of providing exercises to their students, homework, and of course, evaluation of their students. And what do I mean? What I'm talking about teaching robotics, I'm not talking about how to construct the robot, but instead how to teach the concepts behind robotics like perception, action, kinematics, navigation, vision, all those subjects that we are teaching at some point at the universities about robotics. So it's not about the teaching of how to build a robot, but instead about the concepts of robotics that are involved inside robotics. And then you may be asking, so what do you mean that by teaching with the robot in mind? So what I mean is that I don't agree on teaching the concepts just because of the concepts. Then what I mean is that all the concepts included in robotics, they have a reason to be there. And those reasons is they came in the first time from experiences with the robots. So the people, the pioneers that were working with that, they were not thinking about, oh, let me see about coordinate transformations. No, they had a problem with robotics. They have a problem with the robots, and then they figure out on the other direction that they needed this concept, a mathematical concept of coordinate transformations, for example. So I have seen many robotics curriculums say that, okay, so here, welcome to the robotics class, and then you have to learn, on the lesson number 1, we are going to learn computational linear algebra. Okay, yes, nice, it's okay, but let's keep moving forward in robotics. Okay, what's next lesson? Is linear equations and matrices. Okay, interesting, yes, but when do we come to the robotics thing? Yes, so this is robotics things, because in lesson 3 we are going to do matrix determinant. Okay, and then at that point the guys, the students, they don't know what they have enrolled in robotics, because that's not what they wanted to learn. What they wanted to learn is how to do things. So what does all that have to do with robotics? Yes, I agree with you. We know that's very relevant for robotics. I'm not saying that we are not going to teach those things. What I'm saying is that we are going to be teaching when it's related to something that is related to the robotics experience. And for that, you need to start by asking why. So why do I need linear determinant or matrices? Why? And that has to be shown on the robot itself. So I have this robot. I want to do something, and for that I need those matrices, multiplications, and transforms, and so on. For example, this is an example, okay? Then you say to the student, okay, identify how far is the gripper from the object to grasp. This is something that the student is going to understand very quickly, right? Because it's very intuitive. Then for that, you can tell them, okay, let me give you some hints about how to compute this. First, compute the gripper position relative to the center of the robot. Then compute the object position relative to the center of the robot, and then you just compute the difference. And that's also intuitive for the student. Okay, so I know the distance from here to my center, and then from the point to my center, and then is the difference? Yes. Yeah, but the question is then, how do I do that? So, and then is when you come, oh yes, I'm glad you asked me this, because now is when we have to do the matrices. So I have to teach you this concept. But I know this looks like a small difference, but it's a difference that makes the understanding smoother and faster for the students, because it is related to something physical, something in reality, that is how far is the gripper from the object to grasp. And we are solving that problem all the time. So one of the key ideas that I want you to get from this webinar is you have to move into this idea for your creating your lessons. I need the robot to do this for this and that reason. Okay, so I need to compute the distance from the gripper to the object because I need to grasp it. So I need to know how to reach that point and how far I am, if it is reachable, and so on. So that's why I want to compute this distance. And then, how can I solve this problem? How? Oh, very good. Then for that, you can use this algorithm, this math, this technique that somebody else has invented in the past, in the history of robotics. So it's already there. You only need to learn. And they are willing to learn because it has a purpose. It's the math, the technique is not just, the purpose is not the technique itself or the math itself. For a mathematician it is, but not for roboticists. For roboticists it's because I want to solve something, a problem. Otherwise, I don't want to be dealing with the matrices, yes, you know? So that's not the reason why I'm here. Okay, then that's what I mean. So the matrices, the learning of the matrices, or any other mathematical technique or any other algorithm that we need, is not the goal itself, but the goal is to do something with the robot. It could be localized in the environment. It could be follow a person. It could be find the object to grasp. It could be whatever the things that we want to do with robots, whatever. To go over the slope, knock the door, whatever. So this leads to the point that the evaluation cannot be done on the computing of the matrices, but instead of doing the action, in grasping the objects. That is the point that I want to show in this method for teaching robotics with a maximum understanding, because this is rooted in our nature. We understand the things that move and they exist in the space. And when we relate concepts into that, then our understanding is deeper, is clearer, is faster. But then the problem is that in order to do that, we need a robot. So we have to go to the class with robots. It cannot be with some slides with some numbers. That doesn't work. And if you need robots, we can provide it in several ways. One of the ways for me interesting is to provide by using simulations, and simulations with ROS, because a lot of material is already there for you, so you can easily and fast provide those simulations, working simulations to your robot, to your students. And also another one is by adding labs with real robots. So you have, you probably, many of the people that are attending here you already have some robots in your labs, then you need to engage them. You need to take the dust from them and start making the students use them in your classes. Okay, maybe it's not in the class itself because a lot of students, but afterwards, like a homework or an evaluation purpose. That's what I propose. We are going to see in a minute. Then the curriculum has to be prepared in order to make use of both things, of the simulations and the real robots. If you don't have real robots, stay with the simulations. Also, it's okay. I mean, the real robots is because it's even more difficult to make things work in the real robot, and also because the experience is richer for the students. But of course, I understand different labs, different countries, different places, they don't have the budget. It's okay. It's okay. So if you can stay with the simulations only, it's also okay. Then, what I would like to do here, let's see if you have any question on the chat so far, but then if not, or after the questions, then we are going to do together the preparation of a subject, and then we are going to learn how to prepare a lesson that teaches how to do a transformation, a linear transformation, and what about coordinates? What are coordinates in robotics? So we are going to prepare together here, okay? So I'm going to give you the steps, the material, everything I'm going to provide you, so by the end of this webinar, you can go to your class and provide this as a material ready to work. Okay, any questions so far? Let me see. Or give me an applause. Can you see that we can have applauses in the streaming screen? Okay, no questions. Okay, then so far so good. Then let's prepare together this coordinates transformation lesson. Let's see how can we prepare this material based on the teachings that I have shown here, on the teaching methodology that I have shown here. So what we need to prepare is, first, is the lesson of the learning material. Then that's the text, the slides, all the text that explains what you want to explain, and yeah, so that clarifies with the figures, with some code maybe, if it's necessary, whatever it is necessary to teach the lesson. Then we are also going to include a simulation, because this lesson has to be based on the simulation. So the students can see in real time how the simulation behaves based on what the lesson is saying. Then we are going to include some exercises with the simulation. We also provide some homework that they can do at home by using the simulation. And then the evaluation with real robots. I propose to evaluate the students with the real robots, but it could be also with the simulation as well. So how can we put all this together as a lesson for teaching transformations and coordinating robotics? For that, we are going to use a concept that is called the ROS-ject that we have invented here in the construct, and basically it's a ROS environment in the cloud. So we are going to use simulated robots on Gazebo and ROS-based. And everything is on the cloud. We do that in the cloud because it has several advantages. First, we can integrate in the cloud the robot simulation, Jupyter notebooks, and code, and also even the connection with the real robots from the cloud inside a single project. So we can encapsulate all this into one single project. You're going to see in a minute what I mean by that. And also, it's very convenient because, first of all, it will work in all the computers of your students. So if you prepare this material with a simulation that does this and that, once you share this with your students, this will work in your students. But the important thing is that you can share an exact copy of yours, and your students doesn't need to install anything in their computer. Yeah, so because it's executed in the cloud, it's not executed in their students' computer. That means that they can use any type of computer for executing your code, your project, your lesson. And of course, they are free. So you can create ROSjects and provide them for free. So it's shareable, it doesn't require any installation, it can work on any computer, and they are free. So let's go. Let's prepare one of those, and that contains the lesson material, the simulation, the exercises, the homework, and the evaluation procedure. And then let's share with the world. Okay? Great. Then let's go, and let me change now. So now I have to go to this. What is this? Okay, let me delete this because that I don't need this. Okay, so what do you have to do? Please follow with me, okay? First, you need to go to our website and go create an account in case that you don't have. I'm going to put the address to our website here in the chat, okay? So you have to go to this address, the construct.ai. So you go to that address and then log in case that you have an account. Many of you already have. And in case that you don't, then create one right now, a free one, and then start following. So how many of you already have an account? Actually, maybe all of you, because you are watching the stream, and then you can watch this stream also without any account, but it's easier if you have an account. So if you are there, then log in with your account, and then go to the section My ROSjects. So now remember, we are going to create a project that contains all the material for the lesson, and I'm going to teach you how to do that, how you can do later your own lessons. So go to My ROSjects, then click on the option Create a new ROSject. Then in my case, I have 3 options. In your case, you only have probably personal project. Then it's okay, create a personal project. Then we need to select which distribution of ROS we are going to use in this project. Let's select Humble. Please follow me on this case because some things. So let's select the project on Humble now. Then once we have selected that it's going to be using Humble, we can select some simulations already working and provided for you. So those are simulations. So far we have just a few of them, but we are introducing a lot of them in the next weeks also. So we have simulations that are already working, and then you can stay on one of the simulations and see what it contains. So for example, in this case is an arm robot that can do grasping based on vision, spawn objects, control with move it. All this is already provided in the simulation and already working. So hey, wait a second. That's one step, and the other one, which are the 1 and 2, they are already being created so far. Well, not the lesson yet, but the simulation to practice with. You can just click on one of those, and then that will be. So for the project today, for following with me, select the Turtlebot 3. So you click on that, and then select simulation. I see I have Amna that says, when you go to my ROSject, stream stops. I open a new tab and it works now. Yes, that's right. This is right. So it's true because the webinar is in this tab. So it's in this link. So let me open in another link, in another tab. So I'm going to reproduce the problem of Amna. So if you go to the webinar, so you will see this here, right? So now I see myself. I have a stop to prevent this. Then I need to open another tab. So you can keep the stream and then go again to my ROSjects. Okay, so yeah, so here's my ROSjects, webinar, that's it. Okay, I'm going to close my webinar because it's not useful. So, create a new ROSject, select personal project, select registro as Humble, select the simulation as the Turtlebot 3, then put a name. Let's call it Coordinates and Transformations. and then press create. Don't press return. There we have an issue on the GUI. So if you press return or enter, then it will move you back. So press create, and then you will see that a new project has been created for you containing this simulation. So here it is, coordinates and transformations. So that's the one that we have created just right now. Then we need to open it and populate it with our material. The simulation is already there, but we need to create the material, the lesson. So let's open it by pressing run. So now the template for that project, for that DROS project, is being created, including the simulation, a simulation that is already working, and that contains a very nice environment of a Turtlebot 3 and 7-Eleven, it's a convenience shop. So that simulation is already there, running, working. You don't need to launch anything. You don't need to prepare anything. You can just use it. This is very convenient. And what it's doing now is to open the project. So let me know if you have any questions so far or any problems on the chat. What we are going to do now is once it opens, we are going to create the material that explains the lessons of coordinates and transformations. And for some reason, this is taking some long time. I don't know why. It's preparing the ROSJet files. Let's see if it appears. So let me know when it's already available for you on the chat. So here it's opening for me. And now you can see that the first thing that is loading here is the notebook. The notebook is a Jupyter notebook that is the one that will contain our lesson. This is the one that will contain a lesson, and that we can modify, create new ones, and so on. Everything that is convenient in order to create our class. And let me see if it finally loads. So on the background, also, behind this notebook, there is another window that is opening, which is the gazebo simulation. Let me move it here on the side. So both things are loading right now. And let's see when they become available. So here in the gazebo simulation is going to appear the simulation that we have selected at the beginning of this step. So they will be ready with all the topics already publishing, all the controllers running, the environment ready for us to work. And let's see if this notebook loads. So here you can see the notebook loading, and it happens that those things that you can close them. So here what we have is a full desktop environment of a Linux system with ROS installed. So all this is a Linux desktop environment in your browser. And that's very interesting because then the students doesn't have to install ROS in their computers, and they can use Mac, Windows, or Linux computers for doing this. Okay, so far the notebook has loaded, and then the default notebook that loads is a notebook explaining what you can do with the provided simulation. So here is all the information about the simulation that we have selected, and includes some demos. It includes, for example, here navigation is already set up here for that robot. You can control with the keyboard. You can make it appear the camera is publishing. You can see what it's doing with the camera. You can use the RBase to move it, create maps. Everything is running here and providing, this notebook is providing you all the specifications of that simulation, including where are the sensors, the different ones, and giving thanks to the people that made possible this simulation, okay? Then on the other window here, you can see the simulation that has appeared. Let me move back because I'm very close to the walls. Let me move. Yeah, here it is. So now you can see here the Combini shop in many details, and also the robot that is here. This is the robot that we are going to use, and this is the environment in which the robot is going to behave. And here are the details about the simulation. So you can use all those things already working for creating your material, okay? For example, let's say that you want to create a lesson about navigation. Well, here you have already all the things necessary to make the robot navigate. So you can follow the instructions here and then make the robot do a navigation, localize, move around the environment, create a map, etc., whatever it is. So the problem is that the lesson that we want to use today is not this one. So in your case, maybe you can start by editing the cells. You can double click on the cells, and then just modify whatever is there and put your text about your lesson. Right? I have modified this, put your images, put your screen, your commands, your code, whatever. Then for the lesson of coordinates and transforms, I have already prepared some material. Then the material is already prepared. So I have prepared the notebook because otherwise we'll have to write here the whole lesson about this subject, and that takes a long time. Then in order to prevent that, let me provide you the material that I have prepared so you can copy and put it in this project. So how are we going to do this? Because I'm going to copy here the instructions. First is we are going to open the file editor. So here we have on the icons at the bottom, we have one that says code editor. If you click on that one, you can see that is a VS Code web version of it. And you can see here all the files included in this project, So the notebook is included in the notebook's workspace. So that's the files. And those are the files that are defining this Jupyter notebook. But in this case, we are going to substitute the one that is there by default, the one that loads by default. We are going to substitute by the one that I am providing to you. Okay, so follow me on this. Then later you can do more experiment. Okay, so follow me on this one. Then first, we are going to use the IDE to select all the things inside the notebook workspace and select all them, and then right-click and then delete, because we don't want them anymore. We are going to substitute this. Okay, so now the notebook's workspace is empty. So now we are going to upload the file that contains a notebook that explains the lesson about coordinates. This is the one that I have created, okay? So for that, go to the web shell terminal. We are going to open a terminal. This icon here at the bottom that says web shell. This is how we open Linux terminals in our environment. And then if you do an ls, for example, you will see the different directories. So let's go to the notebooks workspace. You see the notebook workspace now is empty, right? Because we deleted everything from the IDE. Now we are going to upload here the file that I'm going to give you. So what we are going to do is to use the wget command and then an address that I'm going to copy and paste in the chat. So let me go there and copy it. So I'm copying this and putting this on the chat here. So the command, let me actually write the full command. Is wget space and this. So let me see, because I don't have the command in this computer. Let me do it by going to the chat myself. So I'm going to copy myself also the command. and then go to the project on the terminal. Inside the notebook workspace, remember, we type the command wget, and then this is downloaded my notebook. So now if you go to the IDE and open the notebook workspace, you will see that there is this star file. It's a compressed file that contains my notebook. Now let's uncompress it. So for that, you need to type this command, tar xvfp, and then the name of the notebook. So let me copy the command on the chat so you can directly copy. This is a typical Linux command to uncompressing. Okay, so let me go to the chat. Put it there. Okay, then let's execute this. And now this has executed and created this default PIB, then the images directory, so everything has been uncompressed. Now I can delete this one, the tar file, by doing a right click and delete, because we don't need it anymore, and it's just using a space. And then the notebook still showing the old files, so we can close on the corner icon and then reopen with the icon on the bottom that says Jupyter Notebook. So now if we open this one, it's going to open the new files. And there it goes. It's our lesson about coordinates and transformations. So here, before continuing, please let me know if you have any problem reaching this point. Here I have a question from Ivo that says, or Ivo Georgiev, that says, the gazebo simulation doesn't start. Should we start it ourselves? No, this gazebo simulation should start by default. It depends on your internet connection, may take a little bit while. Just leave it there, it should appear. And then, you say, never mind, it was just taking time to do it. Yes, that's right. So you don't have to launch anything. So this is in order to make it easier for you and for your students. They just have the simulation there, okay? Then in case that you can close it. Also, you can go to the gazebo icon at the bottom and select Open Gazebo, and then it will get, again, the simulation showing here. There it goes. Any other problems? Amna says it works. Excellent, Amna. Excellent. Yes. Great. So now all of us, because nobody is complaining, but my coffee is complaining that I'm not drinking it, so a little bit. Great. Then now this is the lesson that I have prepared. And as you can see, I'm following the key ideas that I mentioned on the presentation. First, I'm starting with a question about something required for the robot. So how far is the center of the robot from the current position of the center of the door, from the current position of the robot? Because what I want is the robot to get inside the combini. And then I want to know where is the center so I can send the robot to that position and then move through. So the robot will be inside the shop. So that is my goal. Then about anything else, I don't know. I want to know as least as possible in order to solve this problem. That's what I want. Okay, so what do you got for me? Teacher, teach me. So how can I do that? Oh, yes, then for that you need to learn something about coordinates. And then I'm going to explain you coordinates in 2D. And how does it look for a robot from the frames of the robot. So there are two axes that we call the X and the Y, and then how they are located in the robot itself. So for that, there are the concept of frames. And also, I'm introducing that in the robots, we have different frames that are located in different locations. So now I'm showing all those things to the student, and it's based on the robot. It's not a drawing. It's not some figure that I did. It's the robot that is there, that is showing there. Oh, how can I see those things? Very easy. I have put here a command that shows the frames of that robot in the simulation. So in RBase directly. How do we do that? Copy the command. Let's launch it in another terminal. Go to the terminals. So in this terminal, we can launch the command. We can open as many terminals and tabs on the terminals as we want. Okay, don't worry. Then let me launch those commands. No, not that one. Sorry. So we can copy the command, and then launch it for simplicity. So now this is going to launch RBase. And it's going to show automatically, yes. So now this is showing the frames in the robot. And this is in real time. As you can see, that is the laser is being updated. So that's what this robot is experiencing right now. So if I get a little bit back, I can see the whole scene. And now the students, they can understand better those concepts because they make sense on this robot that they can see there. Now I can go and explain about a point in 3D because so far I was in 2D and so on. Then I will explain about the distance measured by the LiDAR and how I can see, apart from seeing here, how can I see the actual values, the numbers, by doing this command. And then when I I get this command, then I will get this information. And then I'm explaining to them that the information is in the ranges. In this array is where the actual information is. And how can those relate to the different angles in the frame of the base scan, which is the frame of the laser. So now I'm introducing this concept of polar and Cartesian and how to convert between them. And then I make an example about computing the distance on the ray that is the first ray, so the first distance, which coordinates related to the base scan correspond. So the first measure around here. Which one are the coordinates, the x and y? So they have to apply, this is an example, how to apply this formula in order to compute this. And then they can understand, oh, it's just in front. So that's a measure that is just in front of the laser of the robot. Oh, that's cool. Okay, great. Then do another exercise and detain yourself. This is an exercise for them in the class. Okay, now compute this, the one for the fifth ray. Where is this located? In coordinates, in Cartesian coordinates. And I put the solution, but not how to compute this. So they have to do it during the class and ask you questions and so on. Then another exercise, the same thing, but compute where is the center of the door. And for that, you can see that the distance of the door increases a lot after some values on the corners. And then that's how you can identify this laser here, ray, and this other laser here. Then compute the xi coordinates of both of them, and then compute the difference between them. In this case, you can explain how to make these differences between coordinates. Then, so that's an exercise that you can make them apply. Then, another thing, it's about transformation. So we have coordinates, a point that is in one frame, and then we need to put it into another frame. So how do we do this transformation? So then here we show how to move from the base scan to the base link, for example, and how the coordinates transform. But then we provide to them some homework that they can do. This is for home. Once you have done all those exercises, all these lessons at home, they can do is to compute the center of the door that they computed before, but put it into the other frame, which is another frame here. So as you can see, we are constructing, but based on all the reality of the robot that is living. And then they have to move the robot by sending command bells to the topic that receives the velocities of the robot. Something like this. Okay, so that's the homework. And then finally, we are going to evaluate with the real robot. So in case that you have some real robots, you can create like a space, something similar that represents the same situation as in the simulation. Then you put your robot, and then those kind of doors, and then they have to detect those points and go with the robot to the central point, the red one. Then that's an example about how to do it. And then you can evaluate them by doing this on the real robot. So then their experience will be experiencing applying those algorithms in the real robot. Then the problem is that maybe some of you don't have a real robot to apply this. In case you don't have, we have prepared a set of robot, a set lab that easily you can use, that is very simple to construct, to build, and then to use in your classes. Let me show you this. So we call this a bot box. The bot box is a warehouse lab in a box. So this, let me show you how it looks like. So this is a set of robots. Actually, there are 3 robots equipped with grippers, cameras, lidars, and sensors. And then they are in an environment that mimics kind of a warehouse with different routes, places to stock all the material, then places where to leave the material, places where to dock, and so on. So we provide the whole material that allows you to construct this lab in very simple steps, and then provide this practice to your robot, to your students. Then you can use this for teaching many, many different subjects, because the robots are equipped with different sensors, it has an environment, it has some materials that some objects that they can detect, identify, and grasp, and so on. So we provide the whole set, so it's easy for you to provide this practice. This is an example of the set. It includes the robots, also the walls that provide the environment, the cubes, the grippers, the floor of the maps that contains the different lines and areas. And also very important for students, for classes, we provide the ROS jets, the ROS projects that allow you to provide these tasks to your students. So they are ROS jets that are making practice directly with the simulation of the environment, and then afterwards with the real robots. So you can make your students switch from one to the other, because the simulation is an actual simulation of the real environment. So they practice on the simulation, those projects, and then afterwards they connect to your robot, to your lab, to the bot box that you have bought. And then you have the students management panel. So we have integrated all this for you. There are different configurations. You can have a look at this website. Let me put the website address here in the, where is it? Here in the chat. And it's very easy to assemble. So here we have Yuhon here that is assembling this. As you can see, it's very easy. This is for the floor, and then put in all the environment. Then you have to build also the robots that come in a box, and then you can, with all the pieces, and then you can build the robot and set all the different parts. Great. So yeah, have a look at those. At this webpage, if you are interested, also to check about the different projects that we have about teaching ROS to basics. So it's making the students practice this, how to make a line follower, how to make navigation, perception, and grasping, and so on. So you can have a look later when you have some time. So now we were here talking about this practice, because so that's the final step that we need with the students. Another thing that is interesting with the BotBox is that we provide the agenda. So you can make your students book the time, and this is automatically managed by the system and allows the student to connect to the robot or not, in case that you don't have a way of managing this. So this is provided, and it's very easy. They just book the time of the day that they want to use the robots, so that there are no fights between the students. Okay, so let me go and show you how to use this here in our project. So it's very simple. I have already done the booking. So the only thing that I need to do is to connect to the robot. So for that, I'm going to this icon that says connect to your robot. I have several robots because we have many labs here, but I'm going to connect to the tortoise bot. So Yuhon, if you can please set the robot there in the environment. Now I'm going to connect. So this is the process from within the project. I am connecting to the robot. And then I will be able to control from my project. That means that I can run my code in the project and then affect the robot. And the implications of these are great, very great, because that means that every student can have its own code, and it is located in its own project, and it's not affecting any of the other students. And they are not actually pushing the code to the robot. They are just connecting to the robot. So the problem, there is no way of the students to crash the robot, to install things in the robot that then the next student is going to prevent them from working. So everything is very clean because every student has its own project. But more than that is that you can have different projects that affect the same lab. And by doing this connection, every project connects to the robot and then does its thing in an isolated way. Well, anyway, so here we have a camera that appears showing me the status of the robot. So this is our environment with the 3 robots, and then today we are going to control this one that is spinning in the environment. And yeah, so how do we do? Then, in this case, what we would do is to launch our code in a terminal. Yeah, so here, in a terminal, we would launch the code in a terminal and then check if our robot is able to reach the center of the door of here. Okay, that's what we would do in this example. So here I don't have the code done, but what I can do is to launch a program to, for example, to tally up keyboard handle, run tally up twist keyboard. So with the keyboard here, I can control the robot that is on the other side. So that would be from my ROSJet, and only myself can I. So now I'm moving the robot with the keys. Then I can make it turn. I can do whatever. So now I'm controlling the robot from my ROSJet, pressing the keys on the terminal. And the same will be with any program, because I can see the topics here. If I do a ROS2 topic list, then I can see all the topics of the robot. Then I can make my ROS programs, connect to those topics and make the robot perceive and so on. So that's how the practice will be provided to your students with a real robot. That's an example, as a way. So, yes. Then, once you have prepared all this material, so remember, you have prepared here the lesson, also you have the simulation, and finally you have the connection to a real robot environment that you can provide the practice, and always following this idea of why do I need to do this? Why? Why do I need to learn? What do I need to learn in order to solve this problem? So once you have this prepared for your students, then you can go again to your list of projects. So I'm going to my list of ROSjects. Here is my ROSject. And then I can share my ROSject with my students. So if I click on this button here, let me show you again. So on the ROSject that I have created, there is a share, this ROSject. You click on this, and then you copy this link and provide to your students. I'm going to provide you my ROSject to yourself, okay, to you on the chat. Then everybody that clicks on that link will get a copy of my project, of this project that I have here, created with you so far. In case that you haven't created because you were just listening to the webinar and not doing the task, just skip the job, it's okay. You can click there and then you will get a copy of my project. And that's how you will share this lesson with your students. So imagine how easy it is. So you have a system that is working with a simulation that contains all the material for the lesson, and you know that everything is working, then you share and you know it's going to work in your students, in their computers, without installing anything. How awesome is this? Then here, let me see. So final point is that in case that you are interested on the warehouse lab, I have put here a code with some discount valid until the end of the month. So have a look and let me know. But now let's go for the questions. In case that you have questions, let me go. So that's the session. Let me see. For example, we have one here from Ivo says, the yellow Lego floor tiles should definitely be difficult for a Totobot to go over. Oh, yes, that is right. So that is why, if you see, let me show on the, where is the simulation? Oh, yeah, the simulation. Yeah. So if you see in this simulation, we haven't put the physics of that tile. So you can see a little bit that the wheels, they get over the small things that are in the ground, in the floor, sorry. So because we didn't put this has physics, this has space. So in order to prevent this kind of behavior, because otherwise it will be very, very difficult for the system. And also it will be more computational difficult. So that will be increase a lot the computational requirements for the simulation, and then you would not see the robot to move that fast. Yes, there is no collision, says Ivo. That's correct, exactly. There is collision with the ground, with the floor, with all the objects around there. There is collision, okay, but not for those specific points on the floor. Oh, by the way, now I am still connected to the real lab. Here, if I want to disconnect for the next student to connect, then just press disconnect, and then the lab is ready for everyone, and then the simulation will be launched again, so we can see the simulation. Questions? Amna says, oh, great, says. Okay, thank you, Amna. Very good. Thank you. Questions? What is not clear? Things you don't agree? Can you connect your own robots? Yes, you can. I have proposed here one solution, which is the bot box, in case that you want to use our already made solution. But for all the things that I explained here, first, you can use everything for free. So you can create the RosJet with the simulations. You can connect your own robots also and provide this to your students if you want. So all those things, they are for free. Then, in case that you don't have robots, then you can use the bot box, for example. What else? Questions? For example, the things that you don't agree about this methodology. How many of you are teachers or teacher assistants or professors? Anybody here, there? Then Ivo says, is the bot box what you have for the master class? And that is the answer is no. So the construct, we are providing a lot of different teaching solutions. And then we have a program that is called the master class, which is 6 months. And then in the master class, we are using more complex robots for teaching because so we need to provide our students with a larger experience. So we are using many different robots. So at the beginning, on the first lessons, you are going to use a robot similar to this one, but it's using another environment. And then you start with this robot, with a Totobot, but then you are going to move to really warehouse robots, so big robots that go underneath the shelves and carry the shelves. Then we have industrial manipulators from Universal Robots with grippers, and then you have to combine perception with grasping with those robots. Then also we have Robot XLs in some other mazes environments. Then we have then a full cafeteria that is with a combination of different robots, including Turtlebot 4 and Universal Robots and other elements like doors that you can control and so on. So more complex. Then Amna says that she is a teacher. And then can you tell me if you do agree with this approach, what you don't agree, what are the trouble that you are having while teaching? What's the reason why you are here in this webinar? Then Ivo says, I was a teacher, but computer engineering, not robotics. Oh, yes. Okay. Yes. That's very interesting because this computer engineering is one of the problems of robotics. So because robotics is more, let's say that it's more populated with people that want to build the physical robots rather than program them. So all the people that build the robots, they want to know, and they know how to program, but it's not their main subject. Their main subject is how to build physically the robots. Then I have found that in general, they lack a little bit of higher skill programming skills, the ones that computer engineering has. So that's what I think that for computer engineers to go there is very good. And then combine the high skills of the mechanical engineers with the computer engineers together in order to create the robots of the future. Then Ivo says the approach is the only one. Great work, guys. Thank you very much, Ivo. Thank you. Thank you. Amna, I still want to know about your reasons why you are attending the webinar, if you don't mind to share. Then Ivo says, eventually my senior class built a 2U nanosat. Maybe, nanosat. Okay, as a satellite, a small satellite. The aerospace companies hired half of the students immediately. Okay, so cool. So cool, excellent. Excellent, congratulations. Congratulations, excellent. Okay, so then I see that there are no more questions, no more comments. Then let's finish the webinar here. It was my pleasure to share this with you. Please start applying this in order to help your students learn faster. So start with the why do we have to learn this and how does applies to the real robots. And I think that your students will enjoy your classes a lot more. They will have a lot of fun, and also they will learn faster and easier. So that's my recommendation for you. If you don't you don't agree, don't hesitate to put it on the comments below on this video, and see you in some time in a couple of weeks with another session where we are going to discover how to create other classes and how to go specifically to the practice with the real robots. Thank you.